set up on our teaching thing. Guess I should share the screen. So you should have my screen now in front of you. I'm a little congested today, so my voice is going to sound even more off than it usually does. If I get too quiet, you'll need to interrupt and tell me. So I'm going to the content repository, and I'm going to go to lesson number 5. There's a lot of readings available. Those are for you to do on your own, as well as you work through the lessons and any of the formal readings. There is a video that was recorded in 2016, and I actually just finished editing irrelevant parts out of that. So that's available. And then this one, today's lesson, obviously we click on it, we get nothing because it doesn't exist yet. And in materials, there are let's see if that's what I think it is. No, it's too small for a... Okay, that's a write-up. So there's some spreadsheets there that are not specifically called out in the PowerPoint part. I'll allude to them as necessary. And let's see, data, okay. This is some explanatory videos for a couple of those spreadsheets. And then there's a section on precipitation notes. So in this case, all the subdirectories have content that would be in your best interest to review. Okay, I got 3 people waiting, so let's bring them on board. 2, 3. That is 5 out of 7, which is not bad. Missing person is Manesh. So, welcome to the few who just joined. You haven't missed anything. I was just setting up the my resources to do the lesson. What I was showing the earlier attendees was that the PowerPoint section has content, data section has content, and the scripting section has content. There's also quite a few readings, and there's a 2016 lecture. I don't imagine I'm going to depart much from this one, so the historical one, you'll be able to catch me in a lie. The description's empty. All right, with that, I've got some notes. I want to make sure I don't miss anything. Let's go through precipitation. Good enough. Actually a pretty efficient file. Let me open my PowerPoint. Open recent. This should be lesson 5. Yeah, this looks right. All right, so the topic of this lesson is the generic words precipitation, point precipitation in design storms. So the lesson does not go into the atmospheric science of precipitation at all. That's well done in the Chow Mei Mint May's book and pretty much any other hydrology textbook. Suffice to say, there's 2 major kinds of precipitation that's atmospheric influence. One are called synoptic storms. So those are behavior that's associated with frontal systems moving across an area. And that's common in Texas and other places in the US, and actually in the world. The other type is cyclonic storms, which we also get. Currently, we're having one right now. I think it was named after somebody, Cristobal or something. One of them swirly things out in the Gulf. From a data standpoint, those two kinds of precipitation systems could be argued to represent two entirely different distributions of data. And in fact, it's usually possible to see that in fairly long-term records to be able to determine cyclonic from synoptic. Nevertheless, they do the same thing. They bring rainfall into our area of interest, and then we would have to ask our hydrologic questions about that. How much of that rain becomes runoff? How much of it becomes infiltration? How much of it is returned back to the atmosphere through evapotranspiration or direct evaporation? So today what I want to focus on is more of engineering hydrology in estimating point precipitation values from online resources or various analyses of those kind of data. And that's going to lead into something called a design storm. So for hydrologic science, this may be irrelevant if you're doing a hydrology question where you're interested in the science of it. These tools are useful for engineering, but they're probably a bit too simplistic for any science questions. And when you get to that point, you'll know. So here's our hydrologic cycle yet again. And now we're interested in the rose ellipse here, where the atmosphere is releasing its water and it's falling back to Earth. Some of it's getting trapped on the trees, some of it's transpiring. A fraction is surface runoff and another fraction soaks into the ground. There's 4 variables of engineering interest. Although I just learned recently that what I know as a variable, they're now called a feature. You can thank that for social media and the programmers taking over the planet. Sort of funny. They won't last forever. The 4 variables of interest are intensity, which is how hard does it rain. Duration, how long does it rain at any specified intensity. Frequency is how often does it rain for any prescribed intensity and duration. And then the 4th variable of interest kind of doesn't fit the other 3, but what's the spatial distribution of a rainfall, either event or climatically or weather-wise, over short or long periods of time? So the first 3 we can answer in a point precipitation sense. Literally, if we have a rain gauge and it's been out for enough years, we can come up with empirical estimates of the first 3 features of interest. The 4th one requires, if we're using gauging, which is not going to be the best tool for it, some way of knowing what the rainfall is at 2 different spatial locations at the same time. And the primary tool recently of that is radar. And a lot of our precipitation models that the weather folks use to tell us if it's... Hi, Nico. You can say hi to the people, or you can get in the way. I hope you're enjoying that little comic relief. That beast you see is called Nico the cat. I've been through this before. He is a 25-pound bundle of cat. What I'm trying to do now is avoid having him sit on the keyboard. And he's really close to it. What are you going to do? We're talking about precipitation. You know what that stuff is. You're going to just stay in the way, aren't you? If we have a rain gauge out and we have enough years of data, it's not too difficult to come up with empirical probabilistic statements to answer what is the intensity, duration, frequency for that gauge. And that's done professionally. And much of that information is then stored in databases, and one of the ones that's of importance is the precipitation frequency data server, which we will visit shortly. And that's a national tool that gives us the ability to estimate these three features. The fourth one's a little harder. I don't have a national tool for that per se. So unlike flood frequency, which we have not talked about yet in this class, but the word frequency and probability are essentially interchangeable in most hydrologic contexts. So unlike flood probabilities, the rainfall probabilities are expressed as a combination of two features. That is depth and duration. They're not, or intensity and duration. They're not considered separately. Because the duration is an important feature of rainfall. It doesn't matter if it rains hard for a very short period of time. It does matter if it rains hard for a long time, or if it rains softly for a long time, then quickly turns into a hard rain, hard intensity, and then stops. Here in Lubbock, we get really good examples of that on the Marcia Sharp Freeway, which is on the north side of campus. Most of you probably know about it. If it gets intense rainfall, and by intense 2 inches an hour, which is not a trivial amount of rainfall, a rate of 2 inches of rain per hour, and if it can sustain that for 15 or 20 minutes, and it happens to be right on top of the Marcia Sharp Freeway, that freeway is going to flood. And then you're going to have automobiles going into the puddles, and it's bad because people wreck their cars and then they have to wade, and they're usually in their party tuxedos or party dresses. It's just no fun. And then there's the mandatory Ford F-150 hike deck pickup with snorkels in it that has to go into the high water to prove it can, and then it gets stuck in the middle. Anyway, I have good video of stupid human behavior in that context. The important thing is, in terms of a total rainfall depth or volume, it wasn't very big, but it was because it was intense and it lasted long enough for the water to pile up and flood the freeways. That's an issue. So that's why the depth and duration are considered together. That consideration reflects that different storms can produce the same total depth, but delivered over much different time frames. And then the subheading here says, consider a slow, gentle rain over a long, long time. Let's say 1 inch an hour for 24 hours, total depth is 24 inches, versus a fast, hard rain, 12 inches an hour for 2 hours. Same total depth. Those are going to be two dramatically different storms from an impact on the environment perspective. So these types of information are reflected in two critters. One's called depth, duration, frequency. The other one's called intensity, duration, frequency. These two convey the same information. So it's a matter of user preference or data availability. The depth of rainfall is the accumulated depth over some time interval. By definition, the duration is that time interval. So if we have a rain gauge that accumulates 1 inch of depth over 1 hour, that would be the 1 hour rainfall, 1 inch. It would also correspond to an equivalent rate of 1 inch per hour. That's probably a bad verbal example, but that's what came to mind. The frequency is the probability of observing that 1 inch in 1 hour. So maybe you're in an environment where that's a very rare behavior. You're out, east of El Paso in the middle of effing nowhere, Texas. It doesn't rain out there much. When it does rain, I mean, it buckets, and then there's pretty dramatic flooding, but there's nobody there to see it, so it's not a big deal. that 1 inch in 1 hour might be very rare out there. So the probability of seeing it happen maybe is 1%, maybe 0.1%. Or if you convert those into recurrence intervals, 1 in 100 chance event. Whereas in the Houston area, 1 inch an hour, 1 inch in 1 hour is not unheard of. It's pretty common, so that might happen with a probability of 25%. One time in 4, you might see a rainfall like that. So we're talking the same depth over the same time, but the probabilities change in that example depending on where we are in location. So frequently, bad word choice. Commonly, these information are expressed in a DDF curve or an IDF curve, which we'll get to shortly. So here's an example of a depth duration frequency curve, and this is pretty much taken from some book somewhere. As a plot, it's pretty typical except for those dashed lines, which are an unusual feature because any of the plots I've seen for engineering design use do not include the error bands. That doesn't mean they don't exist. I've just never seen them. So I consider this an unusual plot. But normally what's done is a family of curves is plotted. In this case, this one's labeled 100, so that's the 100%, excuse me. They're using a recurrence interval. That's better. Of 1 in 100. So that would be a 1% chance event, and 1 in 1,000 is a 10th% chance. And the curves typically look curvilinear parallel to each other. That's not necessarily how the data falls out. The analysts will adjust things as needed because it's our conceptual model that these curves should run as parallel families of curves. So here's a 1% chance curve, a 0.1% chance curve. And then duration is almost always on the horizontal or the left-right axis. In this particular diagram, these are duration expressed in hours. And then the accumulated depth is shown here on the up-down axis. And in this case, the 12-hour duration, 1% chance depth is somewhere around 70 millimeters. And then if we're looking at the 4-hour, for the same probability, 4-hour 1%, a bit over 50. And that's how these curves are presented. And in many instances, the curves are actually expressed as equations, and we'll look at that shortly too. An alternative to a depth duration frequency representation is to represent the magnitude as a rate. And the intensity by definition is the ratio of an accumulated depth to some averaging time. That averaging time is usually the duration. And here is a formula that says that the intensity is depth divided by duration. Now it's not accidental that the duration in that equation presented on your screen has the symbol T sub c, which in other contexts in hydrology means time of concentration. Here, for this discussion, it's some averaging time. And so if you looked at the previous slide, the averaging time was 12 hours. If we now go back to the same previous slide, 12-hour duration, we accumulated 70 millimeters in depth. But if we divided the 70 millimeters by the 12 hours, the average rainfall rate was 5.8 millimeters per hour. Another important concept is the intensity from a DDF curve is not an instantaneous rainfall rate. So we can achieve that 70 millimeters in a variety of ways. We could have a fraction of a millimeter per hour for 11 hours and then 69 millimeters for 1 more hour to get 70 millimeters of total depth. average is still 5.8 millimeters per hour, but that no way reflects the instantaneous behavior. As the duration gets shorter, this will approach an instantaneous behavior. And we don't have measurement tools to do a true instantaneous rainfall rate. Rainfall rates measured at less than 1 minute, I would argue, are probably beyond extremely rare. I don't think it's ever done. The shortest I've seen tabulated by a government agency are 5-minute rains. So anything shorter than that is going to be incredibly unusual. These intensities can be represented in a different kind of family of curves called an intensity, duration, frequency curve. And on the screen is an example of one for somewhere. Again, the family of curves is shown, and the frequency or the probabilities associated with each curve is listed. Here we have 100, so that'd be 1% chance, coming down to 2, which would be 50% chance. 5 is going to be 20% chance. And the way we use these curves is in the same way. So for example, a 20-minute, 20% chance intensity, so 20-minute, we go to the 20% chance curve, which is this orange highlighted thing, and we read across, and it's 5.5 inches per hour. We've got the units right. So that's an IDF curve. Both of them occur frequently, DDF or IDF. We can skip this. This content's correct but obsolete. That's the best slideshow ever. You just skip half of it. So now we're moving on to the national product. So the statement right here, the first bullet item, the sub-bullet, is incorrect. As of October of 2018, Texas is now included in NOAA Atlas 14. In fact, it's NOAA Atlas 14, Volume 11. This is an online tool that produces tables of depths for given geographic locations, and it's called the Precipitation Frequency Data Server. And with any luck, I'm going to click on it, and it's going to fail. That is annoying. We will get to it another way. Precipitation Frequency Data Server. Life jackets. Yay! There we go. Okay, so the blue states are the ones that are currently in the system, and these 1, 2, 3, 4, 5 honorary states in the Pacific Northwest are not part of it yet, and they may not be for a while. So the National Weather Service operates this, and as a privilege to be in the national database, the state actually writes a check to the federal government. And you might imagine that that's not something that states like to do because they feel that they get enough of their money disappeared by the national government. Policy aside, on the upside, it's a central location of point precipitation estimates. I'm going to choose Texas just for grins because all of us are somewhat familiar with Texas, at least by having lived here for few weeks, and I want to call your attention to a few things. So up here at the top, it gives us a choice of what kinds of data are we going to ask for, depth or intensity, and then we have our choice of units: English, metric, Spanish, French, and a few other languages are pending. So in the meantime, English or metric. That was me being a smart aleck. Most of us are probably familiar with English units, even if we think they're dumb. So I'm going to leave that be. And then you have a time series type. One's called an annual maximum, one's called a partial duration. When we study probability, which is at the end of the class, we'll see the difference between the two. So the annual maximum series is a series that's obtained by taking observed data over a year, saving just the biggest piece of that, and then doing that the following year, and the year after, and the year after, and the year after, and for long enough, and then using those annual maximums in the probability estimation model to construct the point estimate. The partial duration series takes a different approach, and it says, I'm going to identify a threshold value. So I'm going to save every observation that's bigger than a certain number. Let's say 1 inch. So some years you might get quite a few 1-inch rains. Other years, not so many. And the partial duration series is thought to produce more meaningful estimates of probabilistic behavior at the frequent events. So at the 50 and 25 and 10% probabilities, the partial duration series is thought to be more accurate. As you approach the more rare events, the 1%, the 0.5%, 10th%, the difference between the two becomes indistinguishable. But I just call your attention because if you're working in a context where you think it's annual maximum and you don't explicitly choose annual maximum, the server tool defaults to partial duration. The next thing you can do is to try to find your location of interest. So it has this list of stations. That's pretty useless. It has an address search. It might actually work, but I wouldn't trust either of those. But if you know the latitude or longitude, or you can move around on the map and place the crosshair on your desired target. And let's go to Houston, just to be different. And so the nice thing about latitude and longitude, I'll show you what the value of that is in a little bit. Okay, so here we've done this. We've moved it to Houston. And it went ahead and looked in its database and constructed a table. The durations are moving down the column here. The probabilities are moving from left to right. They're using an average recurrence interval. So you have to invert these to get the probabilities. Now 1/1 doesn't mean 100% probability. If you read the documentation, it will explain the meaning of a 1-year recurrence interval. And you notice they tend to drop, so I would argue that this column is for specialists. For us, it's useless. So 2 and onward makes sense, and then it has these depths, and you get that from the units. If I want to look at a picture of it, maybe it will make one in my lifetime. Okay, so there's their picture of it. I don't find the online picture terribly useful to me. I do want to point out that once you go beyond 24 hours, behavior changes, and that's not unusual. Let's return to the table. And if we want to download the table, we can either take just the estimates, upper bounds, lower bounds, or everything. I'm going to take just the estimates. I'll hit submit. And the weighting is the hardest part. Let's see what this is going to open as. You see it's a comma save value file. It needs to be filtered. Let's see what happens if I make a subtle file name change. And that's what the table looks like in Excel. And so if you have a need to use it, you can. Okay. So let's suppose we wanted to, let me stop there. Okay, so that's the precipitation frequency data server. The reason it's desirable to have latitude and longitude is if you know the latitude and longitude of your study area, you can access it that way. You actually can access this multiple times by feeding latitude, longitude, download the table, feed latitude, longitude, download the table, and that can be automated. Okay, I don't need you anymore. I think I want to return to the presentation. So there's an older picture of the server. Remember, we just saw that Texas and the Northeast are now updated. Texas update took almost 20 years, so that's why it was like that for a long time. Here's an example with Oklahoma. And moving on. So in 2015, Texas wasn't sure it was ever going to get the update. So they embarked on their own and created a tool called EBD Lookup 2015. And that's now a deprecated tool for Texas. But let's take a look at what it was like. Preferably if I can get control of my computer back. Thank you. Now this is going to take a little searching on my part. You don't have any homework assignment on this, so don't worry about it. You do on the topic, not on what I'm about to show you. So the other way of representing that data is in a equation structure. Let's hope it's running right now. So here's a online tool that fits this. This is a hyperbolic equation. Fits it to tables from the precipitation frequency data server. And it does it based on annual maximum series. And you can choose a state. Let's pick, let's see, who's getting hammered right now? I think Louisiana declared state of emergency because of the hurricane that just hit it last night. So let's go ahead and take care of that. And I'm trying to remember what is Paris and New Orleans is in. Well, that's a funny sounding, Plaquemines Parish. We'll go ahead and do that. And now if we specify a duration, because if you remember that table had duration 5 minutes, 10 minutes, 15, 30, and so on. Did not have a continuous variation of duration, although the plots implied that that's available. Well, what we can do is use this equation, which allows us to adjust the value of t sub c arbitrarily, and it will fit a curve through the tabular information. So we'll go ahead and pick, let's do 59 minutes so we can go back and check it with 60 minutes, which is tabulated. And what it's done is it's gone to its own database, which already has queried the precipitation frequency data server, and it's fit this equation, and it predicts the 50% chance intensity for Plaquemines Parish of 59 minutes. Now let's go back to the server and see if we can try to get back to the main page. Oh, of course not. Releasing in, I want to do Plaquemines Parish, which I may not be able to find. But the look up US. Oh, it's spinning beach ball. Let's go to New Orleans. And I have no idea what parish New Orleans is in. You could look that up. But let's similar close. So this says the 50th percentile, 59 minutes was 2.3 inches an hour. Let's see what the data server shows. We want intensity. We want it based on annual maximum. And we're looking at the 60 minute. This is 2.17 inches per hour. And I'd say they're pretty close. Now, the differences could be that that's a different parish. The 1 minute can't possibly make a difference. But the point being is this is a way to interpolate between tabulated values in the precipitation server. There's another tool that we can use to do that too, which is this one here, log interpretation for the PFDS table. So if you're interpreting the time in the probability table, the linear interpolation is not the correct way to do it. You want to do a log interpolation and then inverse interpolate to recover the value. So if this stupid thing will get out of the way, we're going to do that. We want to interpolate 59 minutes. So we have 30 minutes was 3.21 for the 50th percentile, and 60 minutes is 2.17. Remember, ours was 2.3 by our fancy equation dealy bopper. So if we put the 30 minutes at 3.21, our target is 59, and then we put 60 minutes at 2.17. Let's see what the intensity is by log interpolation. So what it's going to do is it's going to do linear interpolation in log space and then inverse transform back to reality space. And so this claims that 59 minutes would be 2.19 inches per hour for Plaquemines parish. So it'd be worth it for me to find an example where I have the same parish in Louisiana, but I don't know. The Calcasieu parish, I think that's down by Cameron. No, I'm not going to go there. The point is these tools are available. So let's return back to the presentation. Good. Okay, so converting from depth duration to intensity duration is pretty trivial. Intensity duration is the ratio of depth to duration, d over the duration. Conversion from intensity to depth is obtained by multiplication. So the depth is the average intensity multiplied by the averaging time that was used to compute it. So the next step are design storms. So this IDF approach only estimates an average rate over an averaging time. When the temporal behavior of a storm is important, we have to generate hydrographs, time series of rainfall. In design storms, those are statistical models of such temporal behavior, and they're used in hydrology. They're used in our computational hydrology when we have to produce entire hydrographs, hydrograph being the runoff signal. If all we want to do is estimate a peak discharge, we usually can get away with just the IDF estimate. And rainfall distributions are models of the temporal patterns of a storm. And the distribution is also called a hydrograph. And we use these when we're going to generate an entire hydrograph. Before we go there, which is shortly, I want to remind you on the cumulative versus incremental space. So we have these increments that if we were to compute a running sum would produce this cumulative plot. In this case, time on the horizontal axis, depth on the vertical axis. Rain gauges collect stuff on the blue line. That's how rain gauge works. It keeps track of the accumulated depth. Having a rain gauge do incremental is possible, but the data logging program would be a bit complicated. Because what a rain gauge collects is it has a they're called tipping bucket. It has a sensor in it that every 1/100th of an inch of equivalent rainfall that's caught in the gauge, it makes a timestamp of when that happens. So all the gauge is recording is events in time. It doesn't record them every minute, it records them every time the event happens. So when it's raining really hard, there might be a lot of events per minute. And when it's raining really softly, there might be very few events per minute. The programming required to convert that into an equivalent 1-minute catch, not the hardest thing in the world, but it's inefficient use of technology. We can post-process that. So what we do instead is just keep track on the time axis how many events occurred, and on the depth axis the equivalent depth of each event, just add them on to the next one. So anyway, it catches stuff in the blue case. A lot of times we want to analyze it as if we had the red signal, and we obtain that by differencing. We take the difference in 2 times on the blue signal, and the accumulation between those 2 different times is declared the incremental time over that time interval. Now, the distributions are created from historical storms, and then they're analyzed to generate statistical models of rainfall. These models are called design storms. And there's several available. We're just going to briefly look at a couple of them here. The design storm distributions are typically represented as dimensionless hydrographs. So either the time axis is non-dimensionalized and the depth axis is non-dimensionalized, or just the depth axis is non-dimensionalized. And then dimensionalization, you multiply them by appropriate time durations and observed or point precipitation depth estimates to recover the hydrograph. So let's look first at the NRCS type storm. There's 2 of them, a 24-hour and a 6-hour. And then we'll briefly talk about quartile hydrographs. So in 1973, the Soil Conservation Service analyzed depth duration frequency curves to develop dimensionless rainfall temporal patterns called type curves for 4 different regions in the U.S. And the type curves are in the form of percentage mass curves based on a 24-hour rainfall at the desired probability. It was originally intended for use with the SCS curve number runoff generation model, but since it gets used for a lot of other things. Using it for non-SCS curve number is not wrong, but you need to be aware that it was never built for that, and you may need to make analyst adjustments. So the type curve that gets chosen is based on where in the United States you are. So, there's a lot of yellow. So you got the gray on the eastern seaboard, you got a little gray down here in the southeast part of the Gulf, and then you have the left coast, which is brown and orange. Texas is blessed in that we're half yellow, half gray shaded area under the curve. So those are our type curve choices. And then here's what the type curves look like. And I kind of chuckle at this one, because let's return to Texas. So we're either type 2 or type 3. In dimensionless space, type 2 and type 3 are practically on top of one another. Type 2 is a solid one, type 3 is this dashed one. There's a little difference here just after the peak. So the peak part of the storm is at 12 hours in these type 2 and type 3. The type 1 and 1A are over here. They peak at hour 9 and hour 8 respectively. And so what's done in terms of dimensionalization is we choose a particular probability and we find a point estimate for a 24-hour event at that probability. And that value, let's say it's 11 inches, we multiply this 1 by 11. So we rescale this axis by 11 inches. So instead of going from 0 to 1, it goes from 0 to 11 inches. And then anywhere we access it on this, when we read back the cumulative depth at that point. Here's what a 24-hour distribution looks like in tabular form. This is from Chow-Mays on page 461. And there's nothing special about this spreadsheet. It was taken out of their book, which was originally taken from some SCS literature. What is special is I want to call your attention to how time is represented in many tabulations. Now notice it's going 0, 2, 4, 6, 8, 2, 4, 6, 7, 8, 8.5, 9, 9.5, 9, 7, 5, 10. The time spacing is not uniform in these data files. And it's really easy to overlook that. And then here we have some interesting, this looks like some kind of mistake, because you wouldn't expect hour 13.6 to come before 13.5. So I think this is supposed to be a 13. So there's a typographical error right there. But the time spacing is not uniform. So you will have to be aware if you're using these kind of tabulations directly to check that things are occurring at the time you expect them to. And then this is the fraction of 24 hours represented by these particular times. And then these are the weights, or how high up on the 0 to 1 axis you are on the cumulative curve. There are some 6-hour ones available, so the only one I can trace back to something archival is this one in Chow-Mays, where the hours from 0 to 6 are scaled by that relationship. If you encounter a sub-24-hour SCS curve, unless you can trace back the tabulation to an original SCS document or an archival document, it's probably a bunch of junk, and I would advise you not to use it. So to use the type curves, we use some way of estimating the 24-hour depth, and you see I've crossed out some of these older techniques. NOAA Atlas 14 is adequate to set total depth, except in the Pacific Northwest. You'll have to use localized methods. They won't necessarily have a web-based tool, but there'll be maps or tabular information by county. That's not going to be hard if you are doing work there. Then choose an appropriate SCS type curve. That's based on location. And then rescale the type curve with that 24-hour depth to get the design mass curve. And then from that we get incremental precipitation from the rescaled mass curve to develop the design hyetograph. So this goes through an example for SCS type 3 storm in Harris County using 1-hour time increments. And the only caveat would be that we're going to look up something in a DDF atlas, which would no longer be how you do it. You use the precipitation frequency data server. So we look up 24-hour, 25-year depth for Harris County. And then we get the cumulative fraction by interpolating the SCS table. The cumulative rainfall is the product of cumulative fraction times the total 24-hour rainfall. In this case, the total is 10 inches. The incremental rainfall is the difference between the current preceding cumulative and then plot the results of the incremental. You wouldn't have to do that in practice. Well, you probably want to, just to be sure that it looks right, because these are supposed to be balanced storms, so they should have symmetry at around 12 hours. Not perfect symmetry, but they should look kind of symmetrical. So here we're looking up the depth, in this case 10 inches. This is using an older tool, but the modern tool, you would just put the crosshairs somewhere in the middle of Harris County, press delete, boom, Harris County's gone. No, and you get the depth. And so here's the cumulative fraction from the SCS tabulation. This has been corrected for every hour instead of that 13.65 kind of stuff. And then here's the total depth, 10 inches. Done this way. So the P over P24 is from the tabulation. This is how much is accumulated in each of the different time branches. So for example, we get the first 5 inches up to hour 12, and then the last 5 from 12 to 24. And then the incremental precipitation is the difference between the current cumulative and the one just prior to it, and it's assigned to the current block. So this has nothing happening in hour 0. Everything starts in hour 1. There's a reasonable argument that this should be shifted up one cell, and that shouldn't make much of a difference in any subsequent analysis. I'll leave that up to you to decide what you're more comfortable with. And then here's the plot of the incrementals that started from here. We did total depths, and we did numerical differencing to get the amount in each time block. So in block 12, this claims that we get 2.5 inches of depth. In block 13, we get 2.51 inches. And block 14 is probably a little bit over a half. Block 11 over a half. This is a balanced storm, so this has the right look to it. Everything's happening at the middle, and it's pretty symmetrical about hour 12. And that's the SCS design storm. And then this hyetograph would be fed into some computational hydrology tool to answer our next set of questions. What's the infiltration? What's the net runoff? Things like that. We're not there yet. An alternative to the SCS would be empirical hyetographs. So there are empirical hyetographs available for a handful of locations in the U.S. Iowa being one, which is where the methods in this particular document were drawn from. And what these are analysis of many, many real storms with a lot more emphasis on regional behavior, not trying to make something that will work for the entire United States. And one could critique the SCS method in that those maps were based on observations of 90 or 100 rain gauges. And you would think in the US there'd be thousands, but they only had 90 or 100 to work with in the 70s. So there's an awful lot of spatial mumbo-jumbo going on there. This one, on the other hand, has its own spatial mumbo-jumbo, but at least it's reduced in size. And so if you read this document, which is available on the class server, there's lots of words in it. There's lots of equations. There's tables and tables of numbers, because if you can't scare people with words and equations, numbers will usually blow them out of the water. And there's 10 or 15 different graphs. This is figure 11 from that document, and it's the most important figure for practical application. So here is a family of non-dimensional hyetographs. Horizontal axis is time, vertical axis is depth, and there's the 10th to the 90th percentile. A 10th percentile hyetograph what that means is that of the 6,000 observed storms studied, 10% of them would plot below this curve, 90% plot above the curve. The 90th percentile has the complementary meaning that 90% of the storms that were studied followed a trajectory that lied beneath this curve. Maybe it was this curve, maybe it was this one. So the 90th percentile represents most of the observed storms, and you'll notice that the intensity is quite high initially, and then it sort of tapers off. The 50th percentile would be the median behavior of the thousands of storms studied. So it has a initial intensity, kind of a boring part, a little blip here at the end, and then a boring part. The average intensity, as per the intensity equation where it was depth divided by averaging time, if it were plotted on this chart, would just be going from corner to corner. So, a fair question is, well, how can this plot above average intensity and somehow get to the same place? Well, the key is the slopes. So you have a portion of the 50th percentile that has steeper slope than average behavior, and then the remainder has narrower slope, and so that's why it returns to the to this corner. All right, so to use these empirical hyetographs, we need to rescale time and we need to rescale depth. And so the way we would do that would be to multiply the time axis by the storm duration and the depth axis by the storm depth. That's not too hard in words. And the result would be a design storm for a given duration and annual exceedance probability. Now, why the 50th percentile curve? Well, in the report, that was the suggested curve to use for most hydrologic applications. The 90th percentile is mentioned as applicable for cases where you have severe consequences of failure. Maybe a dam would break and that would cause you to get sued and lose your trailer, or a hospital, airport, stuff like that. Mostly the 50th percentile was thought by the authors to reflect meaningful conditions and also capture that storms in Texas tend to be front-loaded. So there tends to be an initial intense part of a storm and then a less intense latter part of the storm. That's not always the case. And what we can't quantify in point precipitation is that storms move. So what we perceive as initial high intensity part of the storm and then a latter lower intensity part really is just could be explained by a frontal system moving across our rain gauge. We have no way to quantify that motion. Radar rainfall is headed that way, but it's probably got a few years to go yet before it's well respected for that capability. So here we have an example with Harris County again. We're using the Texas empirical hyetograph. So we get the depth from Atlas 14, rescale the depth and time using the empirical hyetograph. So here it's done the hard way, which is to directly rescale the plot. So at hour 0, we start at 0. At hour 1, we have about 1.3 inches of depth. At hour 2, we have somewhere between 1.3, and hour 3 is 2.6. Rescaling directly on the graphic is fundamentally pretty stupid, but it is useful to understand what's going on in the tabulations. So it's probably easier to use a tabulation. So in that report, at the end of the report, is a tabulation of time fraction versus depth fraction, horizontal axis versus vertical axis. And so we take the time fraction, we multiply each element of this by 3 hours, and now we have elapsed time. We take the depth fraction, we multiply each element of this by 2.6 inches of depth, and now we have cumulative depth. And when we plot the two, we now have time versus depth, and in this case, a somewhat more meaningful representation of the hyetograph. There was a tool that was built in 2015. The tool's still usable, but because it was part of the EBD lookup study, it's considered obsolete. And in this tool, you would supply the depth and duration and the desired time step increments, so like every 15 minutes. And what it did is it would generate a plot like that, interpolate in the plot so that you would have depths every 15 minutes or 10 minutes, and it was intended for direct copy paste into the HEC HMS program or in the swim program. When we get later on in the course where we're using those two tools, I'll illustrate the use of text Haito, but because it's obsolete, you'd be advised to use the I think it's called interpolate. There's an interpolate function in R to interpolate directly. That way you're not referencing a tool that's been deprecated. So that was all I had for the prepared presentation. I'm going to open it up to questions. And if anyone has questions, now would be a good time to ask them.
Sir, I do have a question over the ES1 assignment.
Do I have a question? Or will I entertain a question? Do you want to ask a question?
Oh, I want to ask a question.
Okay, good.
So you showed us how to use the G3.
Yeah.
Yes, or on Friday. Yeah, Friday. And so I'm not quite sure how to do number 6 on the homework, because I understand the G3 part. I just don't understand how to make the map or like get the area like from that data.
Okay. Let me give me a minute to get to the actual exercise, and we'll do it shortcut style. Okay, so we need to first draw the watershed on this map. And let me go ahead and get a capture of it. So whatever drawing tool you have, you could probably do this in Microsoft Image Viewer. I'm going to go ahead and see desktop. That's bizarre. All right. Looks like it failed to capture. We'll have to try that again. There we go. So there's our map. And so now we have to delineate the watershed. So there's a couple ways to do it. There's superimpose the grid, which is described in the lecture. Since we're in a hurry, I'm going to take a different approach and go from the outlet. I'm going to string a bunch of lines. No particular what these lines, oh, I didn't know they had arrowheads on them. Well, that's okay, we'll just get in the way. Okay, so those are going to be lines that I'm going to move along and try to find high spots. So as I'm moving up along this line, I'm going uphill, uphill, I'm at the top of a hill, and it starts to go downhill. So I'm going to declare that a high spot. There's one high spot. Now if I move along this line, uphill, uphill, down, up, up, I'm at the top of something. Now I'm going down into a different basin. There's a high spot there. And arguably, that's also a high spot. Coming along this way, uphill, back downhill, and uphill a little bit further. I'm having to keep track of which way the water would want to flow. So it's flowing down that way here, that way here. Hard to tell. I'm going to gamble. Maybe that's it. I think that's a little bit too far out. Uphill, high spot, downhill. Okay, so now I will take advantage of the arrows. Water right here is leaving my water. Nico, why'd you just put your butt in my hand? Ah. Okay, if you're going to join us, sit right there. There you go. Good. So now I draw little flow arrows. That's not coming into my watershed. Yeah, it looks like it's going that way, go here. Now I probably have enough to start considering trying to draw a boundary, which is easier if you don't have a cat on your. And right in here is tricky. Yeah, Apple's detected I need to spend money. It's you. Okay, so now we're picking up the recording. So we drew an outline, and it should be on the desktop somewhere. There it is. Placid JPEG. Let's take a look at it. We issue the command a second time. And there's our watershed. So now we need, we have a scale here, 1 kilometer. That's handy. So now we need to put that into our digitizing tool. So let's do that. So now we have to get the file there, and that's going to, see what's the most efficient way to do that. In the interest of time, I'm going to do something that you guys can't, because you don't have the tools for it. But this I think is going to be a lot faster. My web browser. Yeah, we'll try 30% load. Oh, okay, we can go much bigger. Fortunately, you have to do this part by trial and error. Try it at full size. That's enough. And so now we simply need to set our X point, call that a 0. Set our next X point. We can do this in meters, so 1,000 meters. Set our Y point. Back here, set that at 0. Set our second Y point. I'm gonna have to eyeball it. I picked bad points, but that's probably 1,000. So now we've got our axis built. And start digitizing. Save the save the output. So currently it's not allowing that. So sometimes you have to do this over a couple times because the software, it's not allowing me to export. It's easy enough to just quit it entirely. Relaunch. I'm gonna use this square for my kilometer by kilometer. I'll prepare the output first. Then I want to set my axis. And there we go, and we're ready to export the data. We'll go ahead and exit. So now I've delineated. We should have the data file here, which we would open. And it would open faster if the internet wasn't currently in use by 309 million people. I'm going to take this first line out because that was that one point that didn't make sense to me. You shouldn't have to do these manual edits, but if you find when you're doing it that it records a point before you define the axes, you need to go in and take them out. So there's our input file. So 947, 940, 1637, 1645. That's as close to the same point as we can get. Go ahead and save it. And now we can attempt to compute the area. Hopefully I left it, oh I did, I left numerical perimeter laying around in here. Open that with RStudio. Well, that's doing its thing. Let me go ahead and copy this and paste it. Copy. Paste. The only thing I actually don't have is I don't have my reference area. That was a mistake. So we still need to do a digitizing of a reference area. We can do that pretty quick. So I will return to, okay, you gotta go away. You're set to go. Set my output. This time, this one's going to have the name Placid Reference. Okay, X1 right there. And we'll have to edit the first line of this file too, because I have an extra point. Okay, so we're ready to export. Done. We now can exit. So placid reference and placid. Now we'll run the numerical planimeter. And there's a mistake in something. No, I read it correctly. Let's see if I can do this without having to. Oh, I forgot to take that first row out. My bad. Okay, so it's reading the reference correctly. And get negative areas in the. So I have a couple of points that are bad in the Placid Texas file. And so what I would do at this point is I would actually redo both the boundary file and the reference file and rerun it. I should get positive areas. But that's basically how you do the delineation and then use the numerical planimeter. The other way to do that same thing is if you have Acrobat Pro, you can use the drawing tools in Pro directly and just save the scale factor. And that was how you're supposed to do that part of the lesson. And you'll find the internet works better in the evening, or like at 4 in the morning when the bandwidth is high, because this using a shared environment uses an awful lot of bandwidth, and your home internet is the one who's, at least that's the one who's restricting me. 3 hours ago, I could do what I just did right there, and everything would be moved and updated. But right now, it's not functioning. So I hope that answers the question. because I actually am supposed to terminate the call now. I'm beyond the time that I have for you all. Are there any other questions? Or if you want to email me a question, I can address it and just reply to the class. Well, thank you all for staying on as long as you did. We've gone through our whole time. I believe that watershed's not due till tomorrow. The hardest part, if you're using the G3 data tool, is going slow enough to be sure it's setting the coordinate systems correctly. What I did, which was to exit it and then go back and try to draw the same cell, that's where I introduced the negative area. The reference polygon and the measurement polygon have to be done on the same coordinate system exactly. Okay, so that is my cat. If there's no other questions, I'm going to end the meeting now. Is that okay? Nico, you can't hang up on him yet. Funny. All right, well, I'm going to end the meeting now. John, did that answer your question? Or to give you some guidance at least? That's right. Okay, this supplemental video will be how to a quick way to delineate and make the measurements in the placid watershed. So here's the placid watershed here, and we're interested in this outfall point. So we're doing this by hand. We could superimpose a detailed grid system and follow the technique that was described for that. We could try the radial technique that I demonstrated earlier in the lecture, somewhat unsuccessfully because of rushing for time. But this is going to be a small enough watershed. I'm going to use the drawing tool and kind of draw what I think the stream paths might be. And this is based on interpreting the topographic drawings. And here we don't have to be perfect, just good. Maybe up there somewhere. There's this little thing comes like that. Looks to me some undifferentiated one comes like that. There's clearly a path right there. And that would get down to there. Include that. This one here is going the other way. And I'm following the little V's in the topography that indicate downhill, or in my case uphill. So this is not part of our watershed. It goes to here, as does that. This goes this way somewhere. Now, this is a hard call. I don't think this area is part of our watershed, so I'm just going to stop this to about there. And that pond, I don't know if it's in ours. I'm going to include it. So that's about all I have to work with in terms of a dendritic structure of flow to the watershed. So let's go ahead, and I'm now going to draw my boundary. It's going to follow this berm. It's going to go up this hill. Kind of down this ridge line here. Okay, something like that. If I was concerned with slightly more accuracy, I could zoom in and take a look at that way. That's not bad. I'm still uncomfortable in this area, and I think this comes out here a little more, but we're going to go with that. So there's my watershed. I also want to, I'm going to draw my reference right there. And we'll use that to make my reference area. File, save as. Done. Now we're done with that. We want to put it up onto our server. So I'm going to move, you would move it through Moodle. I'm going to move through a different tool. Same concept, but for me this is much faster. And now the slow part because of the pathetic internet at my house. Yay. Now we're going to run G3 data. And resize it a little bit. Wait on the desktop manager to catch up. Open. No. File. Open. There we go. Scroll down a touch. Desktop manager catch up. Okay, let me prepare my output file. There's going to be two. There'll be one called reference. So I'm going to copy the numerical planimeter program into the Placid folder, and we'll just do all the work there. These I'm going to delete. Yes. Hit delete again. Yes. Okay, so now I've got everything set up. I have to use my digitizing tool to digitize the reference and the boundary. I'm going to move the window a little bit. I'm going to resize it. So the move is to center it. The resizing is to give me more working real estate when I get to the act of digitizing. I'll now open the graphic file. I will now open the graphic file. It's requiring multiple instances of the same command, which is somewhat frustrating, but that is the new internet. My phone does the same thing. Although I can execute phone commands with a single try if I include my credit card number with a command. All right, so there's my setup. I'm going to set my export up first. So there's my reference file. And now I need to establish the coordinate system. Oh, it failed to accept the input. So now we're ready to make measurements. We've exported the point date file. We'll clear the file, and then I'm going to change the file name. Now we'll measure the points. So I'm just tracing the boundary. Don't need to overdo it, but we'll get enough points here to, in some sense, get a good representation of the boundary polygon. So this red curve should actually clip that corner. I'm going to leave it be. Our watershed has a little too much area. And we got back to the origin and tried to hit the origin with the last point as best we can. We'll export it. And we can quit the program. So now we'll open our studio with the numerical planimeter already pre-placed in the correct directory. We'll go to Session, Set Working Directory to Source File Location. So that sets the directory Home G3 Data Placid. That's what we want. This one we've already set the okay, so we have the reference and the main incorrect. So this should be Placid Reference as the first file. We can check that it's readable because the second file is the same name, so we should get an area back of 1. Okay, so it read the reference area, we got 1 ratio unit back. So now we take our second file. We'll now change its name to the measurement file name. And we have 1.95 units, and the sign issue is because it has to do with the reference rectangle and the measurement rectangle being displaced in space. The negative data units, I wonder if that's a consequence of the direction that I actually drew the boundary in. But it claims this is 1.95 square kilometers of area. And we can take a look at the actual physical drawing, possibly in our lifetime, and ask ourselves, does this image of the boundary fit in 2 boxes? Well, here's one box right there. And here's a second box right here. And so the watershed indeed fits in about 2 of those boxes, 1.95 to be precise. And that would be how we would determine watershed area.